In this last section of Chapter 8, in 8.4, what we're going to do is we're going to look at how to determine a sample size, or what would be a good size to get a particular confidence interval estimate within a certain error. Now, n is our sample size, and here is our formula. Well, where does this formula come from? If you look back at the first lesson, this part right here is called your sampling error. Let's say that's E. And what we can do is take that part, that's our error, and call that E. And that's our Z value times sigma over the square root of n. And we can just do some algebra to solve for n. To solve for n, what I would do is, I want to get it out of the square root, I would square everything. That takes that square root off, so we have e squared. That's z squared and sigma squared. And I'll just draw a line here, put it under there, that'll be just n. Do some algebra, multiply by n, bring it over here. Divide by e, and this is where that comes from, excuse me, up here. So n is z squared, sigma squared, over the sampling error squared. And the sampling error is just our imprecision and our estimate of the population parameter. So let's just use this formula in this example here. What we have is, we have sigma is 45, we'll need to know that. And we'll need to decide what our confidence interval is and how many points we're willing to be plus or minus, how much error we're willing to put up with. So n is z squared. So for the 90%, it's 1.65. I'm not going to put plus or minus here because when I square it, I get a positive, times sigma squared, all over the 5 points squared. And again, I don't need to put that plus or minus. And when if you get a decimal, which you will in this case, we're always just going to round up to the next whole number. Whether it's 0.5 or less, we're not going to worry about our counting rules. You always have to go up to the next whole number because you can't have, for example, part of a person. So this is always going to be a whole number. Here's another one with our 99%. We want to estimate to within plus or minus 5 minutes. There's our standard deviation. And that gives us the whole number 107 when we round up. If we change it to 95%, again, you see why we always want to have these numbers handy. Have them on a handy cheat sheet so we don't have to look those up all the time because we'll use them a lot. We won't need as large a sample size there for the 95% confidence interval. Okay, now let's look at the proportion. And there's our sampling error. Where does that come from? Well, if we look back in our notes, we had this for the proportion. We had this right here. So that is our sampling error right here. Z square root P times 1 minus P over N. That would equal to our error. We would want to do like we did last time, do some algebra. We would be squaring this. The square would take this off of here. Do some rearranging, and again, set it equal to E. And we end up with this formula here. And you're like, well, Ms. Carpenter, I thought that was little p if we rearrange that formula. Well, they use pi. And yes, pi is population error, and well, we're probably not going to, population proportion, excuse me, I said that wrong, population proportion, And we're not going to know that, so it's going to be based on a sample. For example, in this one, we took a sample and got 0.12. We'll use that for pi in the formula. If we have no clue for pi, we use 0.5 because 0.5 here, which would give me 0.5 here, would yield the largest estimate, and it's better to have the biggest, a bigger sample than you need, if necessary, to be on the safe side. So let's look at this. So we have n, and we're going to have 1.96 squared because of our confidence interval size. Okay, that's our 95%. Well, little p was 0.12. Well, we're just going to assume that the population proportion is 0.12 times 1 minus 0.12. And we're willing to do that within 3%. Now, be careful here. Notice that on the other page we had points. We didn't have a percent. You do need to convert this to 0.03 because it's a percent. It needs to be just a number. So that's 0.03 squared. And when I work that out, I got 451. For this one here, we have 90%. That's 1.65 squared. Again, we're finding n. 38% needs to be written as 0.38 times 1 minus 0.38. And that's over 0.03 squared. And that yields 713. So again, that's our formula, and we're just assuming that a sample or maybe some data from previous situations is going to be a good enough estimate for pi. And again, if we were not given it at all, we could just use 0.5 because that would give us the largest possible n that we could get, and that would be better to be on the safe side.